Okay, so all of this stuff we've been doing, like the whole course so far, I mean, honestly, okay, maybe some of you find it fun, but it's really kind of, in my opinion, a little bit boring because it's just true, false, whatever, whatever. We haven't really done any math, right? Okay, in some sense this is math, but you know, it's. But from here forward, the course is mostly going to be about actually proving mathematical statements. Okay. Okay. Here's something I guess everybody probably knows. So what's an even number? Right? 2 is an even number, 4, 6, 8, right? Basically an even number. So, well, I'll say let n be an integer. So, okay, so we say that n is even if there exists. So you see I'm kind of using a quantifier here. There exists an integer k such that n is equal to 2k. And we say it's odd if there exists an integer k such that n is equal to 2k plus 1. So even if you've never seen this formally explained in this way, I mean, this is what it means to be an even number or an odd number, right? An even number is double of some other number. An odd number is, well, an even number plus 1, basically. Okay. Okay, so let's prove basic proposition. I think it's 2.4.1. So it says if n is even, okay, so n is an integer. We're dealing with the universe of the integers. If n is even, then n squared is even. I guess if I really wanted to write this symbolically, I could say, okay, the universe is integers, integers, the integers. I could say Pn is the statement n is even. And what I'm saying here is for all n, Pn implies Pn squared. I mean, that's a totally equivalent way of writing this proposition. Is that clear? Okay, but as was mentioned, like this is a much nicer way to say it, right? Anyone know how I should start? Well, okay, maybe that's not a well-defined question, but yeah. Exactly, yeah. So what I'm trying to prove is that if I assume n is even, then I want to derive that n squared is even. So you have to start at the beginning, basically start by writing down what it means for n to be even. Yep, which goes back to the definition. So assume or suppose or whatever n is even. So by definition, we can write n as 2k for some integer k. Okay. So I haven't really done anything yet, right? All I've done is use the assumption, or actually I just write down the assumption. So what I'm going to do now is just square n, right? Just take n squared. So because I know how to square a number, so n squared is 2k squared, which is the same as 4 times k squared, which is the same as 2 times 2k squared. And now I claim that I'm done. Can anyone see why? Yeah. Oh. Exactly. Yeah. So I'll say, therefore, n squared is even because 2k squared is an integer. And I can draw a little square. Good. The proof is complete. Right, so because 2k squared is an integer, I've demonstrated that n squared is of the form 2 times some integer. So, yeah, so that proves it. So it's even. Yeah, that's true. So the point here, this is just really trying to clarify that it's because to be even, you have to be 2 times an integer for some integer. And like this is just pulling out the 2 to make it really clear that it's 2 times something with where that something is an integer. Yeah. Yeah. So actually the 4k squared, like, okay, yes, this is even, but it's not completely clear at this point because you know, if I wrote well, anyway, yeah, it's just kind of clarifying that it's 2 times something. Any other questions? Okay, let's prove another thing. So let's prove the converse. Actually, does anyone remember what converse means? So what would be the converse of this statement? Not the contrapositive, by the way, but the converse. Yeah, exactly. Yeah, right. So proposition 2.4.2, which is the converse of this, if n squared is even, then n is even. This time I'm going to, so here we did a very direct proof, right? You know, it's direct in the sense that we started with the first part of the if this, then that, and we drive the second part. I'm going to kind of do this in a slightly different way. I think what I'm going to do is almost equivalent to a proof by contradiction, and you absolutely could do that. I'm going to do something a little bit different, but it's almost the same thing. What I'm going to do is contrapositive. So we prove this, you know, proof by contrapositive. But you could prove this by contradiction, and actually the argument will sound almost the same as doing it by contrapositive. It won't be quite the same, but it'll be quite similar. So I want to prove this by contrapositive, which means I want to prove the contrapositive. What's the contrapositive of this statement? Yeah, exactly. So this is like an if this, then that thing. So, right, P implies Q is the same as not Q implies not P. So we're going to assume not even, n is not even, and we're going to prove that n squared is not even. Yeah, and here's the thing. I mean, I guess we never formally proved that not even is the same as odd, but I think it's kind of, this is another thing which is kind of, we kind of know that, right? So we prove that if n is odd, then n squared is odd. Okay, because that's what the contrapositive says, and that's equivalent to the original statement. Okay, so from this point forward, I'm going to do exactly what we did last time. I'm going to kind of use the definition of oddness, what it means for a number to be odd, and just square the number. So assume n is odd. So n is of the form 2k plus 1 for some integer k. Maybe I'm going to put this here. Oh, that didn't change anything, did it? Okay. I somehow wanted this board to be in front of that board, but that's not going to happen. Anyway, whatever. Okay, so n is 2k plus 1 for some integer k. And now I'm going to square it. little bit harder algebra than last time, but I think this is 4k squared plus 4k plus 1. How do I know that this is odd? Yeah. Yeah, basically this extra 1 is like the key thing, and the fact that this part of the thing is even. So to make it kind of completely clear here, what I want to do is write this part as a 2 times something, which is an integer. And then I can say, therefore, n squared is odd because the thing that's being multiplied by the 2 is an integer. Yep.
Is there a reason why you didn't just take 4k out of the bracket so that it is k plus 1 inside the bracket?
Yeah, I mean, so I could, yeah, you could do that, but then it's not so, okay, then you could perhaps keep working on it more, but so to show that it's an odd number, I just have to show that it looks something like this. It's 2 times an integer plus 1. Yeah, if I factor this differently, like by taking 4k and then writing k plus 1 plus 1, it's not really quite the right format, like the right, structure for showing that it's an odd number. So I kind of prefer doing this because this is clearly 2 times something plus 1, where the something is an integer. And that's, yeah, you have to always keep, yeah, don't just, I would say in general, like if you have these kinds of algebraic things, don't just blindly factor things in different ways. Really keep an eye out, try to know where you're trying to get to. We're trying to get to an odd number, so we kind of know what form we want. So you'll remember last time we proved some stuff about even numbers. So I'll just repeat these because we're going to use them. So we proved that if n is even, so here I'm assuming n is an integer, then n squared is even, and we proved the converse. If n squared is even, then n is even. Okay. So what I want to do now is use these. Well, actually, technically, I think I'm only going to use the second one to prove something for you, which I think, in my opinion, is sort of a more profound, interesting statement. So you probably have heard of these words before, maybe. I don't know. So a real number, x, is rational if there exists, remember what this backwards e means, there exists, integers a and b, where b is not 0, such that x equals a over b. Yeah. And otherwise, x is said to be irrational. Is this familiar? Or actually, I remember when I was like in high school or something, the way I was told, oh, what's a rational or an irrational number? And it was like, oh, it's irrational if the decimal expansion never terminates and never repeats or something, right? But in some sense, that's a completely useless definition because you can't use it for much, but it is true. Yeah, so what we're going to prove is that square root 2 is irrational. So meaning we want to prove that there's no way to write square root 2 in the form a over b, where a and b are integers. Okay. Okay, we might not remember from last time, I guess, but we've done a few different types of proofs so far. So when we proved 2.4.1 here, we did a very direct argument. We did this with a direct argument where we assumed the first part and we derived that n squared is even. This one we did it in a sort of backwards contrapositive way. We assumed n is odd. We proved n squared is odd, which is the contrapositive. So now we're going to see a third method. I mean, it's sort of a method we've seen before in another context, but it's proof by contradiction. Sort of in the same way as when we were doing arguments, like the way proof by contradiction works is you want to prove something. So you start by assuming it's false, and then you do some stuff to derive some other statements, and eventually you get nonsense, you get a contradiction, and therefore you can say that assuming this is false was wrong, right? So it must be true. So in a proof by contradiction, what we're going to do is we're going to assume that root 2 is rational. So root 2 is a over b for integers a and b, where b is not 0, but it doesn't really matter. I mean, okay, and we want to get to a contradiction from this. Now here's one thing we can assume, right? If I write an integer divided by an integer, I can always assume that there's no common factors, right? Because if I write 15 over 21, I can always reduce it, right? I can write that as 5 over 7, right? Right, you can always write a fraction in lowest terms by canceling out the common factors. So let's assume also that a and b have no common factors, because otherwise we just pull them out and cancel them. So we may assume a and b have no common factors. Otherwise, we just reduce we just cancel them. This sounds like a kind of throwaway comment that's unlikely to be useful, but that turns out to be the crux of the whole proof, weirdly enough. Okay, so I'm going to take this equation. I'm just going to square it. So if I know that root 2 is a over b, I can just square it and say that gives me that 2 is a squared over b squared, which tells me that if I multiply by b squared, a squared is 2b squared. So a squared's even, right? B is an integer, b squared's an integer. This shows that a squared is 2 times an integer. 2 times an integer is even, right? So a squared is even. Now I can go back to one of the things we've proven earlier, right? And I can say that therefore a is even, right? Because if a number squared is even, so if n squared is even, then n is even. So therefore a is even. The definition of even is that a number is even if it's 2 times an integer, right? So there exists an integer k such that a is 2k, right? That's just by definition of even. Are there any questions about anything so far? Am I going too fast here? Is it okay? I see what you mean. So here I'm kind of assuming n is an integer. So yeah, square root 2 wouldn't be an integer. So yeah, so I guess above this we should say kind of let n be an integer. And then if it's an integer, then if n squared is even, then n is even. That's the. Any other questions? But that's a good point. Yeah, I should have probably specified the kind of universe I'm dealing with here. Oh, thanks. Okay. So now I'm going to go back to this equation we derived here. I'm going to plug in 2k for a because I can. I mean, a is equal to 2k. I can do that. So therefore, 2k squared equals 2b squared. So this is, so let's say I call this in the box, I call that star. So by star. And so therefore, 4k squared is 2b squared. Cancel the 2, and I get that b squared is 2k squared. So this is just algebra. This looks kind of familiar, right? We've got, we've got something that's even, right? So what this shows is that b squared is even, right? And then we can say b is even because, again, 2.4.2 says that. So this tells me, yeah, maybe here what I should be referencing here, this proposition 2.4.2, and then we're going to use it again. So this means that b is even, which by this proposition means that b is even. We're actually done the proof, but can anyone see why? Yeah.
All even numbers?
Yeah, that's the observation, is that they, now a and b, we've kind of demonstrated that they both have a common factor of 2, but they're not supposed to have common factors. So this completes the proof because, so maybe I kind of want to write this below, but there's no space. But let me say, so this contradicts the assumption that a and b have no common factors, right? By kind of combining the fact that a is even and b is even. And that completes the proof. Yeah, so the way everything seems a bit backwards here, but the way proof by contradiction works is, I start by assuming that this is false, which means I'm assuming it's rational. And then we do, all of these steps to get to a contradiction. So, and our contradiction is that a and b have no common factors and a and b have 2 as a common factor, which is basically kind of a statement and its negation. And once we get to a contradiction, we can say that, our assumption must have been false. So this assumption, therefore it's irrational. So we're trying to show it cannot be written as a over b for integers a and b. We assume it can, we get a contradiction, therefore it can't. So I want to give you one more example of proofs using, well, it's going to use a bit of contrapositive, but also another method as well, which is proof by cases. So this is kind of going to be similar to 2.4.2. It's going to say, so let n be an integer. And it says if n squared is divisible by 3, then n is divisible by 3. Okay. Right. This is very similar to this second proposition, right? Because when I say that something is even, it's the same as saying divisible by 2, right? So really, this is the same statement except for divisible by 3 instead of 2. Is it clear how this is kind of similar? Okay, so what I'm going to do is prove this by the contrapositive again. So what I'm going to do is suppose that, well, maybe I'll let you guys fill in the blanks a little bit. So if I want to prove the contrapositive, what should I assume? And what should I prove, maybe? So do we remember what the contrapositive is? Yeah.
N is not divisible by 3.
Exactly. Yeah. So why did we choose that? Why did you choose that statement? But
Because the positive, like we have like P implies Q, the positive is not Q implies Q.
yeah, not Q implies not P. But yeah, exactly. So if you think of this statement, like if n squared is divisible by 3, you think of that as one open statement kind of thing. Then n is divisible by 3, think of that as another open statement. So this is kind of like saying for all n, Pn implies Qn, where Pn is a statement that n squared is divisible by 3, and Qn is a statement that n is divisible by 3, and the contrapositive is for all n, not Qn implies not Pn. So then, exactly what was suggested, what we should do is assume that n is not divisible by 3, and then derive that n squared is not divisible by 3. So suppose that n is not divisible by 3. Well, if it's not divisible by 3, then if I take a number that's not divisible by 3, and I try my hardest to divide it by 3, I take like a number like 13, and I try to divide it by 3, well, you can think of that as like, it's kind of like 12, right? 13 is kind of like 12, which is divisible by 3, plus a remainder of 1, right? So if you try to divide by 3, you have some remainder. So let R be the remainder when, I don't know, dividing, I don't really know what's the right way to say this, but n by 3. So I kind of know what R is going to be, almost. So what are the two possibilities for R? Yeah. Yeah, exactly. It's got to be 1 or 2, right? Because if it was, for example, if it was 0, then n would be divisible by 3, and that's what I'm assuming isn't the case. So R is 1 or R is 2. R can't be like 3 because then I'm not or R can't be like 10 because, then I'm not dividing by 3, like in a maximum way, right? So R is 1 or 2 because n is not divisible by by 3. Like, so in particular, R can't be 0. But it also can't be like 3 because then I would just put in another 3. Okay, here we've got two different cases. And basically, so what I want to demonstrate for you here is that you can take this proof and kind of break it into two cases, treat them separately, and finish the argument. So we're going to kind of do a sort of proof by cases. So case 1. Okay, so the way proof by cases works is, you get to a point where one of maybe several different possibilities can happen. If you consider each possibility individually and from all possibilities you can get the conclusion, then you know that the conclusion must be true. That's the kind of idea. So here we've got two possibilities, R is 1 or R is 2. So let's first consider the first case, R is 1. So if I try to divide n by 3 and I get a remainder of 1, so n is of the form 3k plus 1 for some integer k. Right, that's what it means for the remainder to be 1. Like 13, for example, has a remainder of 1. 13 is 3 times 4 plus 1. Right? Any suggestions for what I should do now? Do we know what I want to prove? All right, so we're proving the contrapositive, right? I'm assuming n's not divisible by 3. What should I do? Any thoughts? Yeah. Totally, yeah. This is actually kind of the same thing we did in this proposition 2.4.2. Because, like, what do we want to prove? We want to prove that we're assuming not the not of this statement, and we want to prove that n squared is not divisible by 3. So it makes sense to look at what is n squared, right? So just square it. So n squared is 3k plus 1 squared, which is 9k squared plus 6k plus 1. If I'm doing my algebra correctly. Yeah. Yeah, exactly. That's perfect. So that's exactly what I want to do. So I want to take out a 3 from the first two expressions here. So I'm left with 3k squared plus 2k, and I've still got the 1. And what this tells me is that if I take this number n squared, and if I try to divide it by 3, I'm going to be able to put in this many 3's, like, 3k squared plus 2k 3's. And I'm going to be left with a remainder of 1. So therefore, when dividing n squared by 3, the remainder is 1. So n squared is not divisible by 3. And so this completes the proof in case 1. So this completes the proof in case 1. Okay, but it doesn't complete the whole proof because we haven't done case 2 yet. Is this relatively clear? Or any questions about that? This is very much the same kind of thing that we did in the previous proof, or one of the previous proofs. But the only difference is this idea, we have to break it into different cases. Okay. So if you don't mind, I'm going to cover this up, and then we'll do case 2. Case 2 is pretty similar. So case 2 is R is 2. The remainder is 2. So n is of the form 3k plus 2 for some integer k. We're going to do the same thing, right? Just square it. So I should get 9k squared plus, am I right, that's 12k plus 4. It's maybe not as obvious as the previous case, what to do next. Any thoughts? Yep. Right. And then pull out the 3 from everything. Yeah, exactly. Yeah, the weird thing here is the 4, but a 4, just as was mentioned there, 4 is just a 3 plus a 1. So that's exactly what I want to do. I want to rate this as 9k squared plus 12k plus 3 plus 1. And now I can pull out a 3 from everything here. So 3 times 3k squared plus 4k plus 1, and then all of that plus 1. I guess in the previous case, I forgot to say that it's important that the thing inside the brackets is an integer, but I think it's fairly clear that, if you plug in an integer k, then this is an integer. So n squared is not divisible by 3 because when I divide it by 3, the remainder is 1 again. So it's, the remainder is 1. So this, since we've considered all the possible cases, the proof is complete.